Hello everyone, welcome to Digital Electronics and Computer Organization course. I am Sudhakar Ajmera, Assistant Professor, Department of VC, MLR Institute of Technology, Hyderabad. Today we will discuss about applications of K-map, min terms and max terms, canonical and standard forms as a part 2. In previous lecture we have discussed about K-map representations. Next, today we will see actually where K-map is used. So where we can apply this K-maps, that we will see in what field we will apply actually K-maps, right. Next one we will see what do you mean by min term and max terms, and what do you mean by canonical and standard forms, that we will see. And these min terms, max terms and canonical and standard forms are used in designing of circuits. So first we will see applications of K-map, where exactly where we can use these K-maps. So as a part of this we will see K-map is used for simplification of Boolean functions. Okay, while designing any digital circuits we will use simplified Boolean functions. There we can apply this K-maps. So simplification of Boolean functions we will use to minimize the complex Boolean functions into simpler forms, which leads to simpler circuits. Next one, we will apply this K-maps in design of digital circuits, okay, which helps in designing of efficient combinational logic circuits such as adders, subtractors, multiplexers, demultiplexers, encoders, decoders and etc. And which leads these combinational logic circuits are useful in designing sequential circuits like what it is, counters, registers, ALUs and all, right. So there we will use this K-maps. And next one we will use this K-maps in reduction of logic gates. Okay, in any designing digital circuits will require minimum logic gates. So to reduce this minimum logic gates, so we will use this K-maps, so which minimize the number of logic gates required, which leads to reducing cost, size and power consumption. Obviously, because in minimization of this logic gates will reduce the circuit complexity, means there whatever inside components will use, that obviously reduce, so connections will be reduced. So to obtain this will minimize this logic gates. In that reduction of logic gates will use this K-maps. Next one, in the communication we will use K-maps for error detection and correction codes. In the communication often we will send information from transmitter to receiver, okay, while transmitting some information, okay, while receiving, okay, we may lose the data. So where exactly, okay, data was missed, where exactly those bits are corrected, where exactly those bits are missed, there we need to first identify and we need to, okay, that mean we need to detect and we need to correct those bits. So we will use those bits for parity checking, even parity and odd parity. So what I mean to say, in that application also we will use K-maps. Next one, for optimization in PLCs and microcontrollers, for higher applications we will use this K-maps for simplifying control logic in industrial and embedded systems. Next one, for timing and performance improvement also we will use this K-maps. So in timing and performance improvement, how we can obtain this is by simplified expressions which leads to reduction of propagation delay, so that we can improve the circuit speed. There also we can use this K-maps. Not only this, we will use this K-maps for so many applications while designing digital circuits. Next we will see what do you mean by min term and what do you mean by max terms, where exactly these min terms and max terms are useful. Let us see first one, what do you mean by min term. So min term is nothing but it's a minimum term, which is also known as what, product term, in which each variable appears exactly one, okay, either in its true form or complemented form, okay. So next one, it represents a single combination of input variables that makes the function output as a 1. Okay. For example, let us take two variables a and b. Using these two variables a and b, we'll have four possibilities. Okay. Using these two variables, okay, we'll have four possibilities, that is 0, 0, 0, 1, 1, 0, 1, 1. In terms of variable, if you write these combinations, so 0, 0 means we'll take a bar, b bar, next to a bar, b, next to 1, 0 means a, b bar, next to a and b. So 1 means true, 0 means false. So 1 means true means we'll take true value, true variable, and 0 means false means we'll take complemented value. Okay. So this, using these two variables, we'll have these four possibilities. Okay. So a bar, b bar, a bar, b, a b bar, and a b. These are what? These are what? Product terms. These are what? Product terms. Okay. And these are what? Min terms, also called as min terms. Okay. Next one. What do you mean by max terms? So max term is also known as what? Sum term, oftenly odd term. Okay, in which each variable appears exactly once, either in its true form or complemented form. So max terms are used by OR gate mostly, okay, to represent a single combination of input variables that makes the function output as a 0. Okay, in previous case, min term represents a single combination of input variables that makes the function output as a 1. But here represents a single combination of input variables that makes the function output as a 0. Okay, let us take here also, we will take two variables a and b. Using these two variables, we will have four possibilities, 0, 0, 0, 1, 1, 0, 1, 1. But here true values are denoted by, okay, complement, and false values are denoted by true, right, 1. So here 0, 0 means, how we can write here, a, b. Next 0, 1, and we need to take sum among these two variables. 0, 1 means, as I said, 0 means what? Will take a variable as true value here, and 1 means we'll take variables as false value here. Okay, so 0 represent true, this 0 represent 2. So, and in between these two variables we'll take OR operation, because a max term is a sum term. So in between these two variables we'll take OR operation. Like that, if I write all these combinations, so 0 means a and 1 means b, and take OR gate in between this. Next one, here a bar plus b, next one a bar plus b bar, and these are what? Known as what? Max terms, which are used by OR gate, and which is denoted by capital M0. This is what? Capital M1, okay, capital M2, and this is what? Capital M3. In previous case, for min term, these are denoted by M0, M1, M2, M3, small M0, M1, M2, M3. But for max terms, we need to denote with capital M. So these are what? Max terms and min terms, which are used in SOP and POS forms. Let us see next, what is the relation between max terms and min terms, and how it is used in SOP and POS forms. Okay, there are two forms. Okay, one is SOP, another one is POS forms. These SOP and POS forms are used to express any Boolean function. Okay, so both forms describe the same Boolean function in different canonical ways, right? So let us see first one. So what do you mean by SOP form? Means sum of min terms, also known as what? Sum of product form. Okay, this is what? Sum of product form. Sum of product form. This sum of product form, SOP form, will use product term, that is what? Min terms. Okay, so here a bar, b bar, c is one of the product term, a bar, b, c bar is one of the product term, a, b, c is one of the product term. So this product term will be used in SOP form. Next one, product of max terms, also known as what? Product of some form. Product of some form. Okay. This product of some form will use as what? Max terms. Just now we have discussed. Okay. Max term means we'll take variables, okay, which are used by OR gate, right? So A plus B plus C is one of the one of the max term, or what I mean to say, sum term, okay? And A plus B bar C bar is that is also what it is, sum term. This is also sum term, this is also sum term, right? And it is what? Product of sum. So if you observe here, example, F is equal to A plus B plus C. One more term is A plus B bar plus C bar, A bar plus B plus C, A bar plus B plus C bar. These all are what? Sum terms. In between these sum terms, we are taking, okay, product. So this is what? Product of sum terms, right? Next, if you see, SOP represents combinations where output is equal to 1, which uses what? Min term, and for POS form will mostly use what it is? Max terms. Next, canonical and standard forms. What do you mean by canonical and standard forms? So canonical form is a Boolean expression is said to be in canonical form if it is expressed either as a SOP or POS form. So what I mean to say, okay, so canonical form is of two types, that is canonical SOP, canonical POS form. Okay, so in this form, each term includes all the variables in its true form or complemented form. Is known as what? Canonical form. This is not minimized form. Okay, so in this canonical SOP or POS form, whatever input variables are there, all must be there. Okay, so in this form, okay, each term includes all the variables of the function either in its true form or complemented form. For example, let us take, we have two types, that is canonical SOP and canonical POS. Let us take here, input variables are A, B, C for this random function F. Okay, for this, let us say few terms are there, 1, 3, 5, 7. To represent this one term, okay, I took A bar, B bar, C variable, right? So this is nothing but 0, 0, 1. And this is nothing but 0, 1, 1. And this is what? 1, 0, 1. And this is what? 1, 1, 1. So what does it mean? This is 1, 0, 0, 1 means 1, 0, 1, 1 means this is 3, 1, 0, 1 means 5, 1, 1, 1 means what it is? 7. So if you observe this, 1 term, 3, 5, 7 terms, okay, if you observe, all the variables are existed in its true form or complemented form. Okay, if you take this one, term, so how it is denoted? By A bar, B bar, C. So here all these three variables are existed, A, B, C variables existed in terms of what? Either complemented form or true form. So here A bar, B, C. So here also three variables are, input variables are available. Here also three variables are available. Here also three variables are available, but all these are in true form or complemented form. That is what? Canonical form. And this is what? SOP. Okay, sum of product terms. That is why it is what? Canonical SOP. Like that, canonical POS form. Let us take three variables for random function F. Okay, so here randomly three variables are given, 0, 3, 5 and 6. And in POS form, this is nothing but product of sum terms, right? Product of sum. Okay, so these are what? Sum terms. A plus B plus C, A plus B bar plus C bar, A bar plus B C bar plus dot, A bar plus B bar plus C. These all are what? Sum terms. In between these sum terms, I am using what? Product. So this is nothing but product of sum form. To represent this, okay, product of sum form, okay, all the variables are existed in its true form or complemented form. So this is what canonical POS form. So as per canonical, okay, it says that, okay, in this form each term includes all the variables in its true form or complemented form. Whatever input variables we will use, all must be existed. Either it is in SOP or POS, all variables must be existed. Let us see next one. That is what standard form. The standard form is what? It is derived from canonical form. I can say a standard form is a simplified version of the canonical form. It is derived from canonical form, and it is what? Simplified version of canonical form. We will get the standard form from canonical form, right? So in this, each product term SOP or POS need not include all the variables in its true form or complemented form. It is not necessarily to represent all the input variables, right? So it is derived by simplifying canonical form using Boolean laws or K-map, right? And it is also of two types. Okay, so canonical form is of two types and standard form also is of two types. What is that? Standard SOP form, next one standard POS form, right? And this standard SOP and POS forms are derived from canonical form only, because it is simplified version of canonical forms only. And here in standard form there need not be, okay, include all the input variables. So for example, if you see standard SOP form, let us take these are the three variables. Using these three variables, I am taking sum of all this product term. So this is what sum of product term. Okay, here, yeah, here no need to include this one. If you observe standard POS form, okay, standard POS form, okay, here if you observe these terms A plus B plus C, A plus C bar, A bar plus B plus C bar, A bar plus B bar. Okay, if you observe these terms, here each and every term does not have all the input variables, right? Right. So here if you take second term A plus C bar, here in this A plus C bar B variable must be there, but here B variable is not there. So all input variables need not be there to represent these terms. So this is what standard POS form. And here let us take, I am rubbing this one, some typing mismatch is there. Okay, so here standard SOP form means if you take first term, okay, here C variable is not there, so I can say this is what standard SOP form. Okay, so here three variables are there, here three variables are there, here three variables are there, but for this function, okay, first term if you observe, one of the variable C variable is missing in its true form or a complemented form, because okay, it is derived from canonical form. So this is what simplified version, right, of some canonical form. So here one of the variable is missing, so that is why this function is known as what? Standard, and it is in SOP form, right? So standard SOP form, and this is what? Product of all this sum, right? So it is product of sum form, and it is what? Standard. So standard POS form. In standard form there need not be all the input variables to represent these terms. Let us take if one of the example, if canonical form, canonical SOP form is this one, A bar B bar C plus A bar B C plus A B bar C and A B C. Okay, from this if we simplify this one, we will get this function. So in this simplified form, okay, we got from this one canonical form, we got this below function. In this first term if you observe, B variable is missed, and in this second term A variable is missed, and in this third term C variable is missed, because it is simplified version of this canonical function. So here one of the input variables are missed. Okay, that is why it is what? Standard SOP form. So what I mean to say, standard SOP or POS forms are derived from canonical SOP or POS form. In canonical SOP or POS form, all the input variables must be there, but in standard form, there need not be all the input variables. So as of now, we have discussed, okay, applications of K-maps, min terms, max terms. Min terms means product terms, max term means sum terms. Along with this, SOP and POS form and canonical and standard forms we have discussed, right? Because these are very essential in simplifying K-maps, okay? So these terminologies are very essential while simplifying K-maps. So these are necessary. And next topic will discuss minimization rules for K-map and some simplification problems we'll see, right, using K-maps. So there are two forms are there, SOP and POS. Okay, using SOP and POS forms we will simplify some functions, right? So this next topic will see minimization rules for K-map and some simplification problems, right? Thank you.